Welcome back. In the previous sessions, we have seen that there are certain algebraic systems such as groups which serve as the building blocks for the structures comprising the subject algebra. The abstract concept of a group has its origin in the set of mappings or permutations of a set into itself. It is our purpose now to introduce and to study a new algebraic system called rings. The intuition behind rings is obtained from the study of sets of integers on which two binary operations have been defined. In this session, we discuss rings and fields which are algebraic systems equipped with two binary operations. Definition and examples of rings. Definition: a ring R plus dot is a set R together with two binary operations addition and multiplication, which we call addition and multiplication, defined on R such that the following axioms are satisfied. R1, R plus is an abelian group. R2, multiplication is associative. R3, for all ABC belongs to R, the following holds. The left distributive law, A into B plus C equal to A into B plus A into C, and the right distributive law, A plus B into C equal to A into C plus B into C holds. Example 1. Prove that the set of integers is a ring with respect to usual addition and multiplication of integers. Solution: consider Z equal to set of all etc. minus 3, minus 2, minus 1, 0, 1, 2, 3 etc. R1. We now show that Z is an abelian group under addition. Since the addition of two integers gives an integer, addition is a binary operation on Z. Now, we verify the three axioms for a group. G1. If ABC belongs to Z, then A plus B plus C equal to A plus B plus C. Hence, the associative law is satisfied. G2. The number 0 belongs to Z such that 0 plus A equal to A, which is equal to A plus 0 for all A belongs to Z. Hence, 0 is the identity element in Z under the operation addition. G3. If A belongs to Z, then minus A belongs to Z and minus A plus A equal to 0, which is equal to A plus minus A. Thus, for every integer there exists an additive inverse in Z. Hence, Z is a group under addition. Moreover, G4, commutativity, A plus B equal to B plus A for all A B belongs to Z. Hence, Z is an abelian group under addition. R2, for ABC belongs to Z, AB into C equal to A into BC. Hence, multiplication is associative in Z. R3, for ABC belongs to Z, A into B plus C equal to A into B plus A into C, and A plus B into C is equal to A into C plus B into C. Hence, two distributive laws holds. Hence, Z plus dot is a ring. Example 2. Proceeding as in example 1, it can be seen that the following sets of numbers are rings with respect to usual addition and multiplication of integers. The set E of even integers including 0. The set M into Z of those integers which are multiples of some given number M different from 1. The set Q of all rational numbers. The set R of all real numbers. The set C of all complex numbers. Example 3. Prove that the set of numbers A plus B into root 2 where A and B are integers is a ring with respect to ordinary addition and ordinary multiplication of real numbers as the two operations. Solution: let R be the given set, then R is equal to set of all A plus B into root 2 A B belongs to Z. Let A1 plus B1 into root 2 and A2 plus B2 into root 2 belongs to R. Then A1 plus B1 root 2 plus A2 plus B2 root 2 is equal to A1 plus A2 plus B1 plus B2 into root 2 belongs to R, and A1 plus B1 root 2 into A2 plus B2 root 2 which is equal to A1 A2 plus 2 B1 B2 plus A1 B2 plus A2 B1 into root 2 belongs to R. Thus, R is closed with respect to addition and multiplication. R1. It is left an assignment to verify that R is an abelian group under addition. R2. It is left an assignment to verify that if x is equal to A1 plus B1 root 2, y is equal to A2 plus B2 root 2, z is equal to A3 plus B3 root 2 are elements in R, then x into y into z equal to x into y into z. R3. Let x equal to A1 plus B1 root 2, y is equal to A2 plus B2 root 2, z is equal to A3 plus B3 root 2 belongs to R. Then x into y plus z is equal to A1 plus B1 root 2 into A2 plus B2 root 2 plus A3 plus B3 root 2, which is equal to A1 plus B1 root 2 into a2 plus a3 plus b2 plus b3 into root 2, which is equal to a1 into a2 plus a3 plus 2b1 into b2 plus b3 plus b1 into a2 plus a3 plus a1 into b2 plus b3 into root 2, which is equal to a1 a2 plus 2b1 b2 plus b1 a2 plus a1 b2 into root 2 plus a1 a3 plus 2b1 b3 plus b1 a3 plus a1 b3 into root 2, and x into y plus x into z equal to a1 plus b1 root 2 into a2 plus b2 root 2 plus a1 plus b1 root 2 into a3 plus b3 root 2, which is equal to a1 a2 plus 2b1 b2 plus a1 b2 plus a2 b1 into root 2 plus a1 a3 plus 2b1 b3 plus a1 b3 plus a3 b1 into root 2. It can be seen that RHS of x into y plus z and x into y plus x into z are the same. Thus, x into y plus z is equal to x into y plus x into z. Since x, y and z are arbitrary elements in R, this shows that x into y plus z equal to x into y plus x into z for all x, y, z belongs to R. Thus, left distributive law is verified. Similarly, the right distributive law can also be verified. Hence, R plus dot is a ring. Example 4. Prove that the set MNC of all n by n matrices with complex entries is a ring with respect to the addition and multiplication of matrices. Solution. MNC is a set of all n by n matrices with elements belonging to C, the ring of complex numbers. Since the sum and product of two n by n matrices are again n by n matrices, MNC is closed with respect to the matrix addition and matrix multiplication. R1. It is a simple assignment to see that MNC is an abelian group under matrix addition. In particular, the n by n 0 matrix is the additive identity. R2. Matrix multiplication is associative. R3. Matrix multiplication is distributive over addition. Hence, MNC is a ring. Remark. By examples 1 and 2, such E, Q and R are rings with respect to usual addition and multiplication. Hence, proceeding as in example 4, it can be seen that MNZ, MNE, MNQ and MNR are all rings. Example 5. Prove that the set Z4 is a ring with respect to addition modulo 4 and multiplication modulo 4. Solution. Z4 is equal to set consisting of 0, 1, 2, 3. Addition modulo 4 and multiplication modulo 4 denoted respectively by plus 4 and multiple 4 are defined respectively by A addition modulo 4 B is equal to R, where R is the remainder obtained when the usual sum A plus B is divided by 4, and A multiplication modulo 4 B is equal to S, where S is the remainder obtained when the usual product A into B is divided by 4. It is obvious that Z4 is closed with respect to addition modulo 4 and multiplication modulo 4. The composition tables for addition modulo 4 and multiplication modulo 4 are given below. R1. From table 1, Z4 is an abelian group under addition modulo 4. R2. From table 2, the operation multiplication modulo 4 is associative. R3. From tables 1 and 2, the operation multiplication modulo 4 is distributive over addition modulo 4. The above example is a particular case of the following one. Example 6. Prove that the set Zn is a ring with respect to addition modulo n and multiplication modulo n. Solution. The addition modulo n and multiplication modulo n denoted respectively by addition modulo n and multiplication modulo n are defined by A addition modulo n B is equal to R, where R is the remainder obtained when A plus B is divided by n, and A multiplication modulo n B is equal to S, where S is the remainder obtained when A into B is divided by n. It is obvious that Zn is closed with respect to addition modulo n and multiplication modulo n. R1. Zn is an abelian group under addition modulo n. R2. The operation multiplication modulo n is associative. R3. The operation multiplication modulo n is distributive with respect to addition modulo n. Hence, Zn addition modulo n multiplication modulo n is a ring. Remarks. It is conventional to denote the additive identity of the ring by 0. The additive inverse of an element A of a ring is minus A. The sum A plus etc. A plus A having n summons is usually denoted by n into A. Attention. It is not to be considered as the multiplication of n and A in the ring, as in some cases the integer n may not be in the ring at all. If n is less than 0, we let n into A is equal to minus A plus etc. plus minus a for all n summands. We define 0 into a is equal to 0 with 0 belongs to R on the left side of the equation and 0 belongs to R on the right side. Actually, the equation 0 into a is equal to 0 holds also for 0 belongs to R on both sides. The next theorem proves many results similar to the remarks noted above. Note the strong use of the distributive law in the proof of this theorem. These distributive laws are the only means that relate additive concepts to multiplicative concepts in a ring. Theorem 1. If R is a ring with additive identity 0, then for any A B belongs to R, we have 0 into A is equal to A into 0 is equal to 0. A into minus B is equal to minus A into B, which is equal to minus of A into B. Minus A into minus B equal to A into B. Proof. Note that A into 0 equal to A into 0 plus 0, which is equal to A into 0 plus A into 0. Since R is a ring, R is an abelian group under addition, and hence using the cancellation law, we have 0 is equal to A into 0. Similarly, 0 into A is equal to 0 plus 0 into A, which is equal to 0 into A plus 0 into A, implies that 0 into A is equal to 0. This proves property 1. 2. In order to understand the proof of property 2, it must be remembered that by definition minus of A into B is the element that when added to A B gives 0. Thus, to show that A into minus B equal to minus of A into B, we must show precisely that A into minus B plus A into B equal to 0. By the left distributive law, A into minus B plus A into B equal to A into minus B plus B, which is equal to A into 0, since minus B plus B equal to 0, which is equal to 0 using property 1. Thus, A into minus B equal to minus of A into B. Similarly, minus A into B plus A into B equal to minus of A plus A into B, which is equal to 0 into B, which is equal to 0, and hence minus of A into B equal to minus of A into B. To prove property 3, note using property 2 that minus A into minus B equal to minus of A into minus B, which is equation number 1. Again, by property 2, A into minus B equal to minus of A into B. So, equation 1 gives minus A into minus B equal to minus of A into B, which is equation number 2. Now, minus of A into B is the element that when added to minus of A into B gives 0. This is A into B by the definition of minus of A into B. Hence, by the uniqueness of an inverse in a group, we have minus of A into B equal to A into B, equation number 3. Hence, from equations 2 and 3, we have minus A into minus B equal to A into B as desired. Definition. Homomorphism of rings. A function phi of a ring R plus dot into a ring R dash plus dash dot dash is a homomorphism or ring homomorphism if for all A B belongs to R, phi of A plus B equal to phi of A plus dash phi of B, phi of A into B equal to phi of A dot dash phi of B. Remark, in the equation phi of A plus B equal to phi of A plus dash phi of B considered above, A plus B on the left hand side takes place in R, while phi of A plus dash phi of B on the right hand side takes place in R dash. Similarly, in the equation phi of A dot B equal to phi of A dot dash phi of B considered above, A dot B on the left hand side takes place in R, while phi of A dot dash phi of B on the right hand side takes place in R dash. Definition. Isomorphism of rings. An isomorphism or ring isomorphism phi of a ring R with a ring R dash is a one-to-one function mapping R onto R dash such that for all A B belongs to R, 1 phi of A plus B equal to phi of A plus phi of B, 2 phi of A into B equal to phi of A into phi of B. Briefly, phi is an isomorphism from R to R dash. If it is a homomorphism from R to R dash, that is both one to one and on to. Definition. Isomorphic rings. Two rings R to R dash are isomorphic if there is a ring isomorphism from R on to R dash. Example 7. Consider the rings set plus dots and 2 set plus dots. Verify whether the map phi from set to 2 sets defined by phi of x equal to 2x for every x belongs to set is a ring homomorphism or not. Is it an isomorphism? Solution. Since phi of x plus y equal to 2 into x plus y, which is equal to 2 into x plus 2 into y, which is equal to phi of x plus phi of y, condition 1 of homomorphism is satisfied, but if either x or y is not equal to 0, phi of x into y equal to 2 into x into y, which is not equal to phi of x into phi of y, which is equal to 2 x into 2 y, which is equal to 4 x y. So, that condition 2 is not satisfied, hence phi is not a ring homomorphism, hence also phi is not an isomorphism. Remark: if we consider Z and 2Z as two groups, then since condition 1 is satisfied, phi is a group homomorphism, actually phi is a group isomorphism. Some special classes of rings. It may be observed that most of the ring except those of the form M and C seen so far have a multiplication that is commutative. Many of them such as Z, Q and R also have a multiplicative identity. 1. However, 2Z does not have an identity element for multiplication. 2. M and C, the ring of matrices, do have the n by n identity matrix that acts as the identity element for multiplication, but the operation multiplication M and C is not commutative if n is greater than or equal to 2. Definition: commutative ring, a ring in which the multiplication is commutative is a commutative ring. Example 8, the multiplication in the ring Z plus dot is commutative. Example 9, rings that are not commutative. The matrix multiplication in the ring M and C is not commutative, hence M and C is not a commutative ring. Similarly, the rings M and Z, M and E, M and Q and M and R are all not commutative rings. Set 0 as a ring. It is evident that set 0 with 0 plus 0 equal to 0 and 0 into 0 equal to 0 gives a ring. Here 0 acts as a multiplicative identity as well as additive identity. This is the only case in which 0 could act as a multiplicative identity, for if 0 into A is equal to A, we can deduce that A equal to 0. Usually, this trivial case is excluded when speaking of a multiplicative identity in a ring. That is, whenever we speak of a multiplicative identity, we will assume that it is non-zero. Definition: ring with unity. A ring R with multiplicative identity element 1 such that 1 into x equal to x into 1, which is equal to x for all x belongs to R, is a ring with unity. The multiplicative identity element 1 is also called a unity or unit element. Example 10, the ring Z plus dot has 1 as its unity. The ring Q plus dot has 1 as its unity. Example 11, the ring 2Z plus dot has no unity. The following result says that if a ring possesses a unity, it is unique. Theorem 2, if R is a ring with unity 1, then this unity is the only multiplicative identity. Proof: suppose 1 and 1 dash both be multiplicative identities in a ring R. Regarding 1 as identity, we have 1 into 1 dash is equal to 1 dash. Regarding 1 dash as identity, we have 1 into 1 dash is equal to 1. Thus, 1 equal to 1 dash, showing that unity 1 is the only one multiplicative identity. Theorem 3, if R is a ring with the unit element 1, then for any A B belongs to R, 1 minus 1 into A equal to minus A, 2 minus 1 into minus 1 equal to 1. Proof: suppose R is a ring with the unit element 1, then minus 1 being the additive inverse of 1 also is an element in R. 1 A plus minus 1 into A equal to 1 into A plus minus 1 into A, which is equal to 1 plus minus 1 into A using distributive law, which is equal to 0 into A since 1 plus minus 1 equal to 0, which is equal to 0 using part 1 of theorem 1. Now, adding minus A to both sides of A plus minus 1 into A equal to 0, we obtain minus 1 into A is equal to minus A. 2. In particular, putting A is equal to minus 1 in part 1 above, we obtain minus 1 into minus 1 equal to 1. Definition: units of a ring. Let R be a ring with the unity 1 not equal to 0. An element U in R is a unit of R if it has a multiplicative inverse in R. Example 12, since every non-zero element of Q has multiplicative inverse, every non-zero element of Q is a unit. In such, 1 and minus 1 are units as they have multiplicative inverses 1 and minus 1 respectively, but no other element in set is a unit as they have no multiplicative inverses. In particular, 2 belongs to set, but its possible inverse 1 by 2 not an element of set. Attention, never confuse the use of the word unit and unity. Unity is the multiplicative identity, while a unit is any element having a multiplicative inverse. The multiplicative identity or unity is a unit, but not every unit is a unity. For example, minus 1 is a unit in set, but minus 1 is not a unity, that is minus 1 not equal to 1. Definition: skew field or division ring. If every non-zero element of R is a unit, then R is a skew field or division ring. Example 13. Since every non-zero element of Q is a unit, Q is a division ring. In set, 1 and minus 1 are the only units. No other non-zero element in set is a unit. Thus, set is not a division ring. Definition: field. A field is a commutative division ring. Definition: a non-commutative division ring is called a strictly skew field. Example 14. We have seen in the last example that Q is a division ring. Also, the multiplication in Q is commutative. Thus, Q is a field. R, the set of real numbers, and C, the set of complex numbers, are also fields. Example 15. Set is not a field as it is not a division ring. We note that a set F with the two operations plus and dot is a field if and only if 1. F plus is an abelian group. 2. F star dot is an abelian group where F star is equal to F minus set to 0. 3. A into B plus C equal to A into B plus A into C for all A, B, C belongs to F. Subring, subfield. Definition: subring. A subring of a ring is a subset of the ring, that is a ring under induced operations from the whole ring. Example 16. We know that Q plus dot is a ring with the usual addition and multiplication as the two binary operations. Since Z is a subset of Q and since Z itself is also a ring under the induced operations plus and dot, we have Z plus dot is a subring of Q plus dot. Similarly, Z plus dot is a subring of R plus dot. Definition: subfield. A subfield of a field is a subset of the field that is a field under the induced operations from the whole ring. Example 17. Consider R the set of real numbers. We know that R plus dot is a field with usual addition and multiplication as the two binary operations. Since Q is a subset of R and since Q itself is also a field under the induced operations plus and dot, we can say that Q plus dot is a subfield of R plus dot, but the subring Z plus dot of R plus dot is not a subfield of R plus dot. In this session, we have considered algebraic structures with the two binary operations. A brief introduction to rings and fields is made. A more study on rings and fields will be made in the next session. Some more fundamental results will be discussed. Before we attend the next session, please try to answer the following questions. State for which of the following sets the indicated operations of addition and multiplication are defined. The set is closed under the operations and give a ring structure. If a ring is not formed, state the reason. A. Set plus with the usual addition and multiplication. B. N sets with the usual addition and multiplication. C. A plus B into root 2 A B belongs to Q with the usual addition and multiplication. D. A plus B into root 2 A B belongs to R with the usual addition and multiplication. E. The set of all pure imaginary complex numbers R into I for R belongs to R with the usual addition and multiplication. 2. Considering the following rings, state whether the ring is commutative, has unity and is a field. A. N sets with the usual addition and multiplication. B. A plus B root 2 A B belongs to set with the usual addition and multiplication. C. A plus B root 2 A B belongs to Q with the usual addition and multiplication. 3. Describe all units in each of the following rings. A. Set. B. Set 5. C. Q. D. Set 4. 4. Let R plus be an abelian group. Show that R plus dot is a ring if we define A into B equal to 0 for all A B belongs to R. Hope you enjoyed this session. See you next time. Till then, goodbye.